So let's look at the two stages of filtering. And this principle is the same principle whether you're talking about Bayesian filtering of a robot control model, or if you're talking about filtering in HMMs, or if you're talking about Kalman filters. And even particle filters are based on the same principle, just remodeling the actual algorithm in a little different way. So what are the two phases of filtering? The first phase is we're starting filtering with a belief about the world. So this is the belief about the world is really what we believe the probability is for our state. So this would be our probability distribution for our states at time t, p of xt. So this is where we start. We start with a certain idea of what we think our world looks like in a probability distribution. And then the first phase is the prediction phase. The prediction phase is giving our model of how the world changes over time with or without our control input. We have a new belief state, which is indicated here by belief with a little star on top. So we have a new kind of probability distribution. Let me use the right color here. Let's call it xt star, using the same star, which is based on our model of how the world changes over time with or without our control. And then we have the second stage, which kind of goes back to the next time step. And this stage is called the correction. And this stage takes into account evidence. So it takes our intermediate probability distribution or probability distribution over xt, or a new belief or intermediate belief, takes into account the evidence and then updates the belief for the next stage based on the evidence. There are other words for this. So the prediction is sometimes called transition, and it's really based on the transition model, and the correction stage is based on the observation model. So sometimes you'll see words like transition or observation used instead of prediction and correction, or in addition to prediction and correction. And the way that these prediction and correction stages are often presented mathematically is for the prediction we often call this it's sigma of p of x t plus 1 given xt times the probability of xt. And here, this xt here might include also our control, which is usually indicated by the letter ut. And the correction using the observation model is generally referred to as proportional or alpha p of zt given xt times p of xt. And we'll get into more detail of giving us an intuition of why these functions make sense to do the correction and the prediction using a very simple example of filtering. And one thing you can really see here is that this equation up here includes p of xt plus 1 given xt in ut, which is our transition model. And down here, the correction includes p of zt given xt, which is our observation model. That is the model we start with. That's what's given to us in the model and which we use for filtering. Let's look at each of these steps separately using a very simple example. So we're going to put this model in the corner here for reference. And the example we're going to use looks like this. Here's a very simple example. We have a sailboat that's sailing on a one-dimensional world that's discrete. So we have all these different positions, and we are trying to figure out where the boat is. And first we're going to look at this stage, at the correction stage, using our observation model. So here's our observation model. We actually have a very bad observation model. And the observation model, again, that's the probability of any kind of evidence given a state in the world. So here's observation model. We're basically using a satellite camera that has a very bad resolution on our sailboat. And so given that our sailboat is at any point, the camera could equally likely tell us that we're at that point or at the neighboring points. So if, for example, the sailboat is really here, our camera will tell us with 1/3 probability that we're here, with 1/3 that we're here, with 1/3 that we're here. So this is our observation model. This is what we know about our camera, given that we know where the sailboat is. And then we have our current belief. So our current belief is, for some reason, somehow we got to this belief. We might have started with this, we might have learned it over time, but right now at point t in time, our belief is we have a 50% probability of being at this point and 25% probability of being at each of those points. So this is our current belief. This is px of t. This is our model of the observation. So this is our pz of xt. And then now we want to do this correction. Okay? And so here we can see our current belief. And it doesn't really matter if we go first here and then here, because it's an iterative process. But just to see why this equation makes sense. Let's say we got an observation from our satellite that our sailboat was spotted here. So what is the probability of the sailboat being in each of the different slots, given that this is our model and this is our current belief? This is exactly where we just use simple Bayes rule. So we want to know the probability of our sailboat being somewhere given the observation. But what we do know is the observation given the sailboat position, and we also know the prior probability, which is our current belief. So we know from Bayes' rule that this is proportional to the probability of our observation given any particular kind of state and the probability of that state. So this is exactly this here. This is what we basically just know from Bayes' rule. So let me erase this and make this example specific. What is the probability that sailboat is in any of these places? Let's look at one of these places. The probability that the sailboat is in this position should be equal to the probability of getting this observation given that it's in this position, which is 0. Because if it's in this position, we know that 1/3 of the time the observation is going to be here, 1/3 of the time it's going to be here, 1/3 of the time it's going to be here. And the observation is here, so this observation given that it's in this position is 0. So we can really know that the probability here is 0. And it's the same for here and here and here. What about this spot right here? And it could be that the sensor is gone. So here, the probability of this observation, given that this is the correct thing, is 1/3. But the prior probability of this position being true is 0. So this one is also 0. And now we get to the non-zero example. So probability that the sailboat is here equals the probability that it's here in the first place, which was our prior probability, which is 1/4, and the probability of this observation happening given that I'm here is 1/3. So overall, we have something that's 1/12. We can do something similar here, and let's make some room. What's the probability that we're actually here? So we're doing the same thing. the probability that we're here, that we thought we were here, was half. And the probability that if we were here, we would get this observation is a third. So we get 1/6 here. And in terms of the evidence, these two are equal, but in terms of the prior probability, we kind of thought we were here, so we still have a higher belief that we're here, even though the observation is here. And similarly, for here it would be 0, because the probability of getting this evidence, given that I'm here, even though I have a 25% confidence that I'm here, the evidence completely rests the confidence, because no evidence is ever wrong by 2. So we have these two probabilities, and now we normalize them. And normalizing them will give us 2/3 for this and 1/3 for this. So even though our evidence is here, our prior probability of this being the correct state sways us towards this probability distribution. So basically we're doing exactly what Bayes' rule tells us to do. We want to know what is the probability that we're in a certain state. We're asking, well, what is our prior probability that we thought we were in this state? And given that we're in this state, what's the probability that we would have gotten this evidence? And this gives us, through Bayes' rules, this new probability distribution. So let's draw that in instead. One important thing to notice is that the evidence actually made our probability more precise and more confident in one of the states. It makes our probability sort of narrower, because evidence gives us more information and therefore makes our beliefs generally more precise. Next, let's move on to the prediction state and replace our observation model here with our prediction model, and see why we have to sum and we can't just use Bayes' rule directly. So here's our transition model. As you can see, I took away the evidence because we're now not dealing with evidence at all. We have a very simple transition model. If we're at any point on this line, there's some wind, and this wind drags us forward one point in time with a probability of 3/4 and 2 points forward with a probability of 1/4. So this is a wind that we know with 75% chance to move us one step ahead, but with a 25% chance it can actually move us 2 steps ahead. In this case, it's easy to see that there's 0 probability to be here, and it's 0 probability to be in any of these 3 states because they're just too far away for our model. But what's the probability for these other time steps? Let's look at one of them, for example. Let's look at the probability of being here. So the probability of being here is really using the law of total probability. The probability that I was here in the first place and then moved here, and the probability that I was here in the first place and then moved here. So let's write this out. Okay, we want to know the probability of being here. So the probability of being here is the probability that I was here in the first, I was right about this guess, and that would be P of being here, so that would be 2/3 times the probability that I moved 2 steps ahead, which in our model is a 1/4 probability, plus the probability that I was actually here, which was 1/3, times the probability to just move 1 step ahead, which is higher, so it's 3/4. So overall, that probability is precisely, it's 1/6, here it's 2/12, and here it's 3/12, so it's 1/6 plus 3/12, 1/4, and that equals 5/12. Okay, so the probability of being here is 5/12. Let's look at the probability of being here. The probability of landing, and here, let me fix this. The probability of landing here is, again, the probability is that I was here in the first place, so that would be 2/3, that I moved 1 step ahead, which is 3/4, plus the probability that I was here in the first place, and moved 0 steps ahead, which is really 0. The probability total here is 6/12 or 1/2. So let's call this 6/12. And then lastly, it can be easily seen that there's really no probability that we're here, because if we were here, we moved either 1 or 2 steps ahead. If we were here, we moved either 1 or 2 steps ahead, so we couldn't have stayed here. So the last probability, the last part to sum this up to a probability of 1 would be the probability of landing here, which is the probability of 2/3 times the probability that we moved 3 steps ahead, which is 0, plus the probability that we were here in the first place, times the probability that we moved 2 steps ahead, which is 1/4, which equals 1/12. So this is how we compute the prediction step. We can see that for every one of the prediction steps, we have to look at all the possibilities. And this is why we have a sum up here. We have to look for all the possibilities and then predict based on the possibility. So this equation here, really, that's what it tells us. It says for each one of the current probability distribution possibilities, take the probability of this and then take the probability of the transition. And we'll see how we factor in control in the next stage. But right now, let's redraw our probability distribution based on our prediction step. Here we can see the new probability distribution, and we can see it's actually more spread out than the previous one. And this shows us also a commonality of the prediction step using the transition model, which is that it makes us less confident about the state of the world. So the prediction spreads out using the probability distributions that we have, spreads out our confidence, because we're almost, we're just guessing in the dark without having any evidence about what the next step could be. And so our next observation step will again narrow our, using evidence, narrow our probability distribution. And so let's move this out of the way for a moment. As a final point, I would like to talk about how we integrate control into this. And basically, it doesn't change anything, because all we do is we have a more complex transition model here. So let me exemplify this. Let's say our control, UT, can be one of two things. We can either add a motor, like pull the throttle on our sailboat and make it go faster, or we could just let the wind do its thing. So let's say we have two kind of control possibilities here. So now we can see we have one option where we're activating the motor. So that would be the opposite here. We have one option where we just let the wind do its thing, so it's like a zero control action. And this is the same model we had before. And we could activate the motor, which flips our probabilities here in this case. So if you activate the motor, you have 3/4 of a chance to get 2 steps ahead, 1/4 of a chance to get 1 step ahead. And then we would rephrase this probability distribution here and call it given xt and ut. So it's just a more complex transition model. We would do exactly the same. We would basically go over each of the probability distribution possibilities, and then, because we know if we did or didn't activate the motor, that's the action that we're doing, we would choose either this or this one when we do the prediction step. So we would say, what's the chance of ending up here, given this current belief, and us using the motor. So we'd say it's the probability of this times the right probability from this, because we know that we're on this stage, plus the probability of this times going 1 step ahead, plus the probability of this going 3 steps ahead, which is 0. So really the control doesn't change anything. And as a final reminder, filtering is described as continuously updating a belief, giving a sequence of evidence and control. So we are given U0 and then evidence 0 and then U1 and then evidence 1, and then U2 and evidence 2, etc. So at each step we're given these two values, and we use the control value to choose the right transition model, and we plug it into this, basically summing up over each of the possibilities of our current belief. That creates our intermediate belief, which is this updated belief, which we then use as the basis, as the prior distribution for using Bayes' rule to update each of these, taking into account the evidence, basically looking at the probability of this particular evidence that we're seeing given our intermediate belief. And that is how filtering works. This is how Bayes filters work. This is how Kalman filters work. This is how H&M filtering works. And this is, if you think about it, exactly what the particle filters do, except that instead they don't compute these probabilities precisely, but instead they use sampling to represent these probabilities through a proxy of particles.